Hello, ladies and gentlemen. Welcome to our uh, lecture on data analytics. Today will be a shorter lecture, let's say part one of causal modeling techniques, because, well, I was unable to get slides for this talk in a level that would be acceptable for me. So I decided that I will split it in two to get something at least today and follow that later, perhaps on Wednesday. Uh, so generally, today we'll start to cover the general ideas considering causal modeling and how to create our models. This is very important aspect of your projects because this will be something that is a necessary part of each of the projects. Causal model, a DAG representing your data generating process and relationships between inputs, outcomes, and variables that are measured and non-measured. So we'll try to explain certain ideas and also address certain issues that are problematic in the context of projects that are being submitted from the previous years. And generally, let's start with the main question: why really we want to do some causal modeling? It comes from the general idea that we rely on data to make some predictions, but those predictions don't tell us what will happen if we take an action. This is let's suppose there is a classic example. There's a website called Spurious Correlations, and you can observe certain things that can strongly correlate with one another. For example, we have a number of people who drowned by falling into a pool, and a number of films that Nicolas Cage appeared in a given year. So, as we can see, this number is those values are highly correlated. The correlation is over 66%, so this is significant. However, obviously, those things are not related. Nicolas Cage cannot force people to drown in their pools by just appearing in a movie, especially in the period of since 1999 till 2009. So, if we would want to create a predictive model based on this information, then we could get a good fit for a historical data. But for example, if Nicolas Cage would not appear in any movie, then in the following year, then would the drowning fit? Probably not, because the changes are not related, they are just correlated. So what we should look for in modeling of processes is to find those causal relationships, to construct our models in a way that explains relationships not based on what is correlated with what, but what causes what. And that, of course, is much more difficult problem. And we discuss this because causal modeling is a very natural fit to the Bayesian analysis. Because in Bayesian analysis, we incorporate our prior knowledge, for example, from the domain experts. We can then infer our prior beliefs about causal relationships. We can know when the data are limited or noisy, and we can compensate with that using using some kind of information encoded in prior distributions for given values. And moreover, Bayesian inference will give us a way to quantify uncertainty in our conclusions, which is crucial when our decisions have any kind of real consequences. So Bayesian analysis is very good in when you want to use your model to not only predict something what will happen as a observable event, but what would be the consequence of inaction. And if your model is based on correlations and not causation, then, for example, you can have an issue with getting models that provide you with very bad predictions. And integrating both those things in Bayesian reasoning gives you potential to create more robust, more efficient models. So, how the causal modeling can be represented. So, for example, we can use that in across any discipline. It helps us in diagnosing faults in complex systems, which is really obvious situation that we can see the cause of the causal chains of events happening. For example, if sensor fails, we can skip the we can miss the overheating of certain aspects, which will lead to a shutdown or a failure of a mild failure of the device. So analyzing the faulty system or diagnostics of systems, creating a causal relationship will allow us to find a way to incorporate proper information that we are collecting into our essential model. And this is all even more relevant in the context of control systems, because all control systems are naturally causal relationships. The causal relationships control systems are very easy because we know how inputs influence state of the system, how state influences outputs, and even we can understand how disturbances come into the system and how they influence depending on the model. So we can consider causal models as a certain more abstract idea of constructing relationships, more abstract than typical control block diagram when we see how control signals follow. We can analyze much more supple relationships, not necessarily starting with determination of how something causes what, as in control system, but more what causes what, so where there is a relationship. In biology, we can easily find such effects, ideas like, for example, what happens when certain drugs affect certain genetic aspects, which leads to recovery. So we can have a causal relationship there. In economics, it's the causal relationships are less understandable. We kind of have issues where to understand how, for example, tax rate we influence consumer spending. We know that the relationships is there, but how these relationships works, it becomes much more complicated. And that again would lead to more complicated relationships with employment. Now we can observe issues happening with the tariff policies of United States, where we can see that we can certainly say that tariffs cause changes in the economy, in the markets, but what kind of changes there? Well, that is a bit more complicated. So, what really we want to know? Causal inference helps us answer three classes of questions. Associational. So, what goes with what? interventional, what if we do this, and counterfactual, what if we had done something else. Each step requires stronger assumptions and more careful reasoning. And we will use directed acyclic graphs as tools for modeling of the structures of these complex relationships. Generally, prediction is something that is the easiest aspect of what can happen, what we can understand what's going on. This is the more typical aspect of creating models, that we take certain variables that are observable and use those variables to predict certain values. Intervention is more complicated because when we intervene, we change certain values in a way that can be more that is separate from our that ignores the naturally happening situation. So, for example, when we increase the amount of pesticides in the area, we create an intervention. We change certain variable that was previously related to some other actions. For example, when we are considering agricultural projects, we want to consider elimination of pests in our crops, and there were some observations. We measured some pesticide levels that come naturally from the surrounding areas. We can see what happens when we observe that. And when we create an action here, then that action is no longer just prediction, because our prediction model is based on naturally happening situations that come from some kind of complicated ecosystem of things happening. If we introduce intervention, we change something. We change something, not changing what caused that thing we've changed. We're just changing it by direct action. And that requires stronger assumptions and a better understanding of causality than just predicting situations. Because in predictions, we can hide sometimes behind correlations. Correlations can have a very good predictive properties. However, if we decorrelate something by changing it independently of other naturally changes, then our model need to be causal to address that. But this is only the aspect of capturing proper causal relationships on variables that we can intervene on. If, however, we want to change something that we usually do not have any influence on, then we can move to counterfactual situations. So, for example, what would happen if it would rain more? How would our situation become if we had more rain in our system? So that's a completely different situation that might be related to even more aspects. This is called a Pearl's ladder. Pearl, and actually Julia Pearl, is a scientist that is very responsible for a lot of advancement in certain aspects of causal analysis. He specializes in use of directly acyclic graphs and so-called do calculus, which we will not cover extensively. However, the idea is to understand relationships using DAGs, direct acyclic graphs, and to understand. So here, as we can see, the more complication arises when we move up in levels of those ladder. Association, the easiest one. We'll see and observe, and from these observations of certain variables, we want to predict something else. intervention, so we can consider the aspect that we can intervene on, and counterfactuals is something that we don't use this word in technical sciences too much. However, it is perhaps a bad thing, because this is more imaginative analysis of our model, how our model would work in different conditions. What would happen if something else happened? What would be happening in this is a very subtle subtle it is very subtle uh, difference between intervention and analyzing of counterfactuals, but we could kind of think of intervention in from automatic control point of view. We can understand the what is the that intervention is a control signal, and analysis of counterfactuals is, for example, how would this control signal would work for a different system, for a system with different parameters, with a higher friction coefficient, with larger resistances, with smaller resistances, with some kind of imbalance, etc. So that would we kind of can observe. So what is really important is that when we move along this ladder, in association, we can often rely on just data-driven simple models. We just can fit something to something and we'll be happy with that. And probably we get, sometimes even get better results. However, the more we move towards intervention counterfactuals, our model have to understand the situation better in order to get something reliable estimates of the intervention or effects or considerations in a counterfactual environments. Our main tool in the analysis of causal relationships will be a directed acyclic graph. In short, DAG. DAG is a graph that has nodes which represent our variables we are interested in. Those might be measurables on unmeasurables, and edges which represent direct effects, how something influences something directly. What is important in DAGs is that DAGs are acyclic. That means that this is the A, that causal relationships flow in only one direction. And DAG is the most abstract model in this case because it allows us to encode just assumption about causal structure, not particular nature of these effects. What is important that in DAG there are no feedback loops. The causes don't loop back to influence themselves. So this is important in the context of DAG, that what is that this is only a structural relationship. And DAG is not built from the data. This is a very important aspect that you need to understand. It is a model of how we believe the world works. It implies certain statistical independences which can sometimes be tested by analyzing data. The independences come from the concept of something called de-separation. And the idea is that if we do not, for example, if we have a DAG like this, A influences B through C. If we do not condition on B, C is dependent on A. However, if we know the value of B, we condition on the B, so our model relates on B, then this path is blocked. If we know B, A and C are independent from each other. So-called conditional independence. And we can think about it in statistical ways, but generally, if we know something, we can ignore. If we know something that directly influences the result, sometimes we can either ignore or do not analyze directly the intermediate cause from the beginning. As a reminder, DAG is not a data. DAG cannot be created by analyzing a correlation matrix, which is something that you do rather often in your projects. So try to remember that and focus and do not repeat that mistake in the future. DAGs are built from the domain knowledge. For example, in an engine system, we have a fuel that influences the combustion. Combustion influences the power output, which can influence the temperature, which can, if uncontrolled, lead to engine failure. What is, however, important is that when you create your DAG, you begin with your intuition, because this will allow you to construct these relationships. The more knowledge you have about the problem, your intuition will be better. If you don't have a knowledge, you can look for books, for references, for certain relationships. And what is important, we do not try to overcomplicate our diagram. We shouldn't add arrows unless we have some rationale for them. Because, for example, we can think, well, there might be some relationship between fuel quality and temperature. But what kind of relationships? Why it comes here and why it's not covered by the combustion process? You need to have a good justification from that in order to provide it. The problem that generally happens in DAGs and modeling is something called confounding. Confounding is something that influences both the treatment and the outcome. These are certain common causes which influence at multiple aspects. And that can be a very problematic, because if we do not account for confounding, we do not consider what's happening, then unfortunately we can introduce an association that is not causal, that is just observable. And that leads us to certain common causal structures. There are main three structures that are present in the analysis of diagrams. We have a chain when A causes B, which causes C. It is also called a pipe. We have fork when B influences both A and C. And we have a collider when C is influenced by both A and B. So, for example, chain structure can be interpreted as when there is observed weather conditions that can lead to wet road, which can lead to traffic accidents. A and C are associated. If we condition on B, we can block that association, because at least part of it, because if there is wet road, we know that there's a higher risk of traffic accidents. There might be additional effects caused by visibility, but those are different aspects that can be or not related. That's why B, or the middle of our chain structure or pipe structure, is called a mediator because it mediates the effect of A and C. So for example, we can have a situation where we have bad weather conditions but still dry roads. But the visibility is small, so there's still more traffic accidents. So certain aspects of effect of A can be captured by B, but not necessarily all. Let's make a more complicated examples with some numbers, so you can kind of understand what's going on. So let's consider the problem of web advertisement. Our X variable is the amount of money spent on digital advertising. Z is the number of website visits generated by that, or generated while that money was spent, and sales is a revenue generated from those visits. So we can easily understand that ad spend influences sales by driving web visits. Because, or mostly that, because if we provide the digital advertising, that generally leads to clicking on a website. If we don't click on the website, there will be no visit. Our data generating process is very simple, just so we can analyze something. We get a randomly generated ad spends, because it's always standardized, so it's not a problem. So we get this generated ad spends as normal distribution distributed at X. We generate website visits as certain proportion, 0.8 time spent money on distribution, and the sales as 60% of visits. This is a very significant relationship, but we will not be going there. So by our construction, ad spends and sales are correlated by our change X through Z to Y. Web visits is a mediator. It's an our pipe or other pipe in a chain between ad spend and sales. We will consider very simple regression modeling. We will try to create a linear model that will regress Y on X and Y on X and Z. As you've seen here, our true data generating process did not directly include X in Y. So if we model without the mediator, just spend money on sales, we have a simple regression like here. In case of our conditional model, we regress both on Y and X. So, if we use the most basic ordinary least square regressions, just to get a number here, we could use Bayesian analysis, but that we will just get histograms instead of that. So for our purpose today, we'll just focus on standard ordinary least squares because that's easier. So if we have this unconditional model, we have very strong relationship between ad spend and the sales. However, if we condition on both X and Z, then the relationship of those two things can become, then this relationship becomes much smaller. And without controlling for the mediator, the web visits, the ad spend appears to predict the sales. So we can assume, using our simple model, well, if we know our values of, we know how much we spend, so the more we spend, the more we gain. However, in our conditional model, the coefficient on x is almost 5 times smaller and with negative sign. But this is a very small number, so we could assume that it is generally there is no relationship. At least we can expect that, because I haven't shown here the confidence intervals, but those confidence intervals might not be very nice. So with the mediator in the model, the direct link from ads spent to sales vanishes or diminishes. It's showing that all of that ad spend effects runs through web visits. So conditioning on the middle node blocks that indirect path. So no direct association remains between the ends of the pipe. So what does it mean? That means that using this model, we cannot, using our most simple model, we might have a problem if we wanted to propose the action for advertising. So using the unconditional model, we have natural, okay, we spend more, we will earn more. That's what our model is giving us. However, in case of conditional model, we see that if that money will not influence the web sales, the web visits, we will get nothing. So our model is very dependent, or our business model is very dependent on how effective that ad spend campaign will be on attracting new web visits. And perhaps if we could introduce different way of getting new views, then that will change our predictions more effectively. So this is a very simple structure, a very simple idea. In practical model, we will have a lot of pipes, we will have a lot of relationships that can happen, and that's why it's very important to analyze them in order to find certain aspects that happen here. Second structure, fork, comes for this, this one has a standardized name in all literature as a fork. The central node B is a common cause for A and C. And if you look at the data, A and C will appear to be correlated, even if there is no direct link. This is classic case of confounding. Once we condition on B, A and C will become independent. And this is what we called previously D-separation. In causal analysis, identifying and adjusting for this kind of common causes is very critical to get unbiased inference. If we do not condition for such things, we will have significant issues when considering our models in order to provide some necessary action. Because if we just see that A and C are correlated, so we will change A and the C won't change, then we'll have a significant problem. More detailed example. Let's consider an example from chemistry. We have a reactor, and this reactor we have a temperature in degrees Celsius. And temperature influences both reaction rate and viscosity. The higher temperature, the viscosity becomes lower. However, the higher temperature in the reaction, consider the endoenergetic reaction, the temperature will speed up the reaction. So, temperature simultaneously influences both of those things and is a co-founder that can cause a naive association between X and Y. Let's again create a data generating process. So, we get a random sequence of random temperatures and we generate viscosity samples as a normally disturbed linear relationship. So, the viscosity drops with Z and with temperature, and reaction rate rises with temperature. There is no causal link between viscosity and the reaction rate, besides the fact that they both depend on temperature. And again, we will consider two examples. Unconditional model, which will regress y on the x alone, and conditional model, which we will regress y on x and z. In this way, we can have the relationship we can consider without observing or controlling for the co-founder, and with introduction of that additional information. So as we can see, things can significantly change. Coefficient for viscosity and its influence on reaction rate, if not introducing the confounder to the model, just based on creating the relationship between viscosity and the reaction rate, is strongly negative. If we ignore temperature, we can conclude that changing viscosity causes changes in reaction rate. And we could perhaps try to do some other viscosity changes. This is main risk on working on data only. If we observe certain relationships and we do not understand what those variables mean to each other, that's why we did not create some kind of causal structure, we can introduce significant problems in our computation. However, both variables were driven by temperature, and if we introduce the temperature to the model, then we can clearly see that the dependence of reaction rate on the viscosity is negligible. So if we control in our model for this stem of our fork, so our temperature, we can block this spurious association. Returning to Nicolas Cage movies and drownings, perhaps there was some special moonstruck effect on people that made them both at the same time drown and finance more Nicolas Cage movies. There might be some unknown confounder. Confounder might not necessarily might be known, but that's why we need to analyze the models and analyze our assumptions and create proper interpretations in order to be safe that our model makes sense and will not lead us to conclusions that are not supported. Final structure we'll discuss today is the collider. Collider is more irritating case because it can introduce certain problems. Because collider is a case when A and B are initially independent, but if we condition on their common effect, they became statistically associated. This is called collider bias or selection bias. So, for example, if we condition on people who receive a job offer, so if we analyze only people that receive the job offer from the pool of all the candidates, it might appear that experience and education are negatively correlated even if in general population they wouldn't be. This is a very common mistake in observational studies. If we condition on a collider, and unfortunately we might condition on the collider without our knowledge, because we might receive the data set that already during data collection introduced that conditioning. That can open a path that shouldn't be open, that open relationship that is not really there. More detailed example, let's consider recruitment for studies. We have exam results and we have extracurricular resumes, so like some extra credit points, some awards, etc. And we have admission score, the university composite admission score, which is which school computes as a weighted sum of exam and the extracurricular activities. So Z is a linear combination of those two aspects. If we would like to create analysis between exam results and extracurricular activities, we can create a simple model. And we now know that X and Y are independent. People who pass their exam are not, or got high results on the exam, not necessarily, it might be completely unrelated to their extracurricular activities. Because, for example, someone was collecting lots of credit because of their or extra bonus points because they had problems with getting academic results. So those things are unrelated. The relationship should be zero. However, if we get a conditional model and we will regress on both the admission score and the exam score, then we will have a spurious association between X and Y. So B1 will be generally different from 0. For example, if Z would be a binary variable, then we will have selection bias, so we just consider on people who pass the exam. We could have a relationship that is not really there. And it might not be. If we create an unconditional model, so for all the populace of candidates, we analyzed Y and X, we got the very small relationship. It might be negligible. If we, however, introduce conditioning on the result of the exam, then we will have an issue. The relationship will be there and will be negative, more strongly negative. Colliders are tricky and colliders can be problematic when analyzing our models. So, we will end on this point today. Our main takeaways to remember are that causal models are not correlations. They are here, so we will not get fooled by correlations that might happen because by confounders, or might be effect of selection bias, or might be hidden with pipes. So those things might be problematic. We've covered those 3 basic cases, which we will then build upon on our second part of the causal analysis lecture, and we will get to it later and we'll try to discuss how we can introduce that to our Bayesian models. But this part is relatively important for the lecture, for the projects that you will be creating later. Thank you very much for listening today, to all those that listened, which was, I've seen, up to 3 people, at most 2 at the same time. If there are any questions, of course, feel free to ask them if they're on the chat. If there are not, we will be finishing in a moment. Okay, thank you very much. No questions. So have a good night.